Hello students, in this chapter we are going to discuss the second part of the complex numbers. Let's first define the equality of two complex numbers. Suppose we have the given complex numbers, say z1 is equal to a1 a plus iota b and z2 is equal to x plus iota y. Then z1 is equal to z2 if and only if the real part of the complex number z1 is equal to the real part of the complex number z2. Similarly, the imaginary part of the complex number z1 is equal to the imaginary part of the complex number z2. That is, z1 is equal to z2 if and only if a is equal to x and b is equal to y. Then we can say these two complex numbers are equal. For example, we have a question like this: find the value of x and y if x plus iy is equal to 2 plus 3i. It is given that here these two complex numbers are equal. We have to find the value of x and y. As per the above definition, two complex numbers are equal if their real parts and imaginary parts are respectively equal. Here we can say these two complex numbers are equal if x is equal to 2 and y is equal to 3. So here we get the value of x is equal to 2 and y is equal to 3. Let's do another example. The example number 2 is again find the value of x and y if the complex number x plus y plus iota times x plus y is equal to 2 plus 3i. So here we have to find the value of x and y for which these two complex numbers is equal. So as per the definition of the equality of two complex numbers, here the imaginary part, this is the complex number, this is of the form of a plus ib. So this is the real part, that is x plus y is the real part, and x, say here x minus y is the imaginary part of this complex number. So here x plus y, the real part of this complex number is equal to the real part of this complex number, that's 2. And this is the imaginary part, x minus y is equal to 3. So this is first and this is second. We have to find the value of x and y, so we have different types of methods, either elimination method, either cross multiplication method or substitution method. Here solving first and second, we have x plus y is equal to 2, x minus y is equal to 3. So adding these two equations here, we get 2x is equal to 5, that is x is equal to 5 by 2. Similarly, if we subtract these two equations, we get here 2y. If we subtract these two equations, we get 2y is equal to minus 1. So y is equal to minus 1 upon 2. So these are the two values of x and y. Therefore, x is equal to 5 by 2 and y is equal to minus 1 by 2. Let us define another term, that is, you have to remember modulus of z square can be written as z into z conjugate. For example, if we have a complex number z is equal to a plus ib, we know that its conjugate is z bar, that is a minus ib. So z into z conjugate is equal to a plus ib into a minus ib. So this is equal to a square plus b square. So here we will find the mod of this complex number z. So mod of z is equal to square root of a real part square plus imaginary part square, which implies mod of z square is equal to a square plus b square. So keep this is the first and this is second. So looking first and second here, z into z bar is equal to modulus of z square. So sometimes we may write z into z bar is equal to modulus of z square. And also this point, remember, modulus of z is equal to modulus of z bar. So these are the two important terms that you have to remember, because if when we go concepts of circle, we may here you have to remember these two. Here you have to remember these two results. These are the two important results. Now what is the geometrical representation of complex numbers? Remember x comma y, an ordered pair x comma y represents the complex number in argand plane. In argand plane. So what is argand plane? This is same as the Cartesian plane. So in argand plane, the real numbers are taking along x-axis, and the imaginary numbers are taking along y-axis, and this is the origin. So every ordered pair in argand plane, you have to remember in argand plane, y-axis represents the imaginary line. Imaginary line. This is the imaginary line. Along imaginary line, we are taking the imaginary numbers. For example, x comma y, xy represents the complex number in argand plane. So if x and y both are positive, then it lies in first quadrant. Say this point, x comma y. X, and this distance is y. Therefore, we can say here this is the point P. Point P represents a complex number. Say point P represents a complex number x plus iy. In the same way, if we say a comma b in argand plane, a comma b in argand plane represents a complex number a plus ib. Here iota y, this is the imaginary, y is the imaginary number. So imaginary number is taking along y-axis. Thus we can remember here, or we can say imaginary numbers are taking along y-axis. That is why this y-axis is known as imaginary line, and this x-axis is known as a real line, because the real numbers are taking along real axis and the imaginary numbers are taking along imaginary y-axis. So x comma y represents a complex number x comma y. So this point is A. So OA is x and AP is y. As we know that this angle is 90 degrees. So join this. So what is OP? What is OP? So using Pythagoras theorem here, OP is square root of x square plus y square. This is nothing but it is the modulus of this complex number. This is the modulus of this complex number. So this is equal to mod of z. So in geometrical sense, mod of z represents here OP. This is the length from O to P. And this OP makes an angle with x-axis, say theta. And this theta is known as argument. This is known as argument or amplitude. Argument or amplitude. So, this point, say z is equal to x plus iy, represents a complex number in Argand plane, and mod of z is equal to OP, that is equal to root x square plus y square. So what is the conjugate of this complex number? That is x minus ry. So this represents a point that is x comma minus y. So x comma minus y plus minus lies in fourth quadrant. So this is this point. Say this is the point Q. This is x minus y. So conjugate, this is x plus iy, and this is x minus iy. Actually, the conjugate x minus iy is the conjugate of the complex number x plus iy. Thus, we can say this is the mirror image. This is the mirror image of complex number. Thus, z bar is the mirror image of this complex number along x-axis. So thus we can remember here every complex number in Argand plane, every ordered pair in Argand plane represents a complex number. For example, if we say 2, 3 in Argand plane, this 2, 3, this is the ordered pair, this represents a complex number, that is 2 plus 3i. In the same way, if we have point minus 1, 2 in Argand plane, we can say this is the complex number. This is minus 1 plus 2i. So every ordered pair in Argand plane represents a complex number. Therefore, x comma y represents a complex number in Argand plane, and x comma y represents a point in Cartesian plane. So here we are talking about Argand plane. Thus, say this is the point x comma y in Argand plane, therefore it is a complex number x plus iy. This distance is y, say this is a, and this is the origin, this distance is x, and this is the modulus of z of p. This is the modulus of z, and this angle is 90 degrees. So if the point lies in first quadrant, if the point, or in other words we can say if the complex number lies in first quadrant, then this angle, say this is theta, this is known as the argument of complex number and is denoted by ARZ, argument of complex number, or sometimes known as amplitude. Amplitude. So, if the complex number lies in second quadrant, say this is say point Q, this is x minus x comma y. So this is minus x plus iy. This is again mod of z. This is 90 degree. This is length x. This is y. And this angle, that is this angle. This is, if this angle is theta, then this angle is pi minus theta. Thus, pi minus theta is the argument of this complex number. So, if the complex number lies in third quadrant, then this angle, this is pi plus theta. If this angle is theta, this angle, then whole angle will be pi plus theta. So, if the complex number lies in third quadrant, then the argument of the complex number is pi plus theta. In the same way, if the complex number lies in the fourth quadrant, say this, then this angle is the argument of this complex number. This is 2 pi minus theta. Or in other words, we can say the amplitude of the complex number. Now, how to find the argument or amplitude of a complex number? Let's do some examples. Consider an example. For this example, we will learn how to find the argument of the complex number. For example, find the argument of the complex number. Z is equal to 1 plus iota. So here, the imaginary part of the complex number is positive, and the real part of the complex number is positive. Thus, we can say this complex number lies in the first quadrant. So, its geometrical representation is like this. Here, a real part of complex number is 1, and the imaginary part of the complex number is also 1. OP. This is the complex number 1 plus I. And we have to find this angle. That is the argument of the complex number, theta. Now, we have to find this angle, theta. This distance is 1, this distance is 1. To find the argument of this complex number, we know that this is an acute angle. So here the argument of z is theta. So argument of z, that is theta, is equal to tan inverse of modulus of b upon a. If the complex number lies in the first quadrant, then its argument is tan inverse of modulus of b by a. So here the argument of z, that is the angle, that is tan inverse of 1 upon 1, which is tan inverse of 1, which is pi by 4. So this is the argument. Because here this angle also, here this angle, this is 2 pi plus theta. This is also the argument of this complex number. This is also, that is 4 pi plus theta, the argument of this complex number. Thus, we can add here 2 and pi. So, pi by 4 plus 2 and pi is the argument of this complex number. 2 and pi plus pi by 4. Now, if we have a complex number like this, say z is equal to 1 minus I, we have to find the argument of this complex number. So, first we will see here 1 minus I, that is plus minus, lies in 4th quadrant. So, this is the point, 1 minus 1. So, this is the argument of this complex number. And this is 2 pi minus theta. So, here the argument of z is 2 pi minus theta is tan inverse of modulus of b upon a. So, this is 2 pi minus tan inverse of minus 1 by 1. So, which is equal to 2 pi minus pi by 4. This is 8 pi minus this is equal to 7 pi by 4. So, this angle is 7 pi by 4. This angle may be also the argument of this complex number. So, we can add here 2 and pi. So, argument of this complex number is 2 and pi. Argument of this complex number is 2 and pi plus pi by 7 pi by 4. Here the complex number is z is equal to 1 plus I, but here the complex number is z is equal to 1 minus I. The modulus of these two complex numbers is same, but the argument is different. Here the angle is, the argument of this complex number is pi by 4 plus 2 and pi, but here the argument of this complex number is 2 and pi plus 7 pi by 4. If we change this complex number again, now let's take the complex number here, z is equal to minus 1 plus I. First complex number was here, z is equal to 1 plus I. And its argument was 2 and pi plus pi by 4. And second complex number we take 1 minus I. And its argument was 2 and pi plus 7 pi by 4. Now we have taken the complex number z is equal to minus 1 plus I. So this complex number lies in second quadrant. This is minus 1, 1. And this is the argument of this complex number. That is pi minus theta. Now to find theta, you have to remember theta is equal to tan inverse of modulus of b by a. So here the argument of this complex number is, pi minus tan inverse of b by a, that is tan inverse of 1 upon minus 1, which is pi minus pi by 4, which is 3 pi by 4. So the argument of this complex number is 3 pi by 4. But if we take the second round, third round, fourth round, here, say this complex number, like this. This is the first, after second round, this angle, and after third round, this angle, and after fourth round, this angle. So therefore, in general, we can add here 2n pi. So argument of this complex number is 2n pi plus 3 by pi by 4. That is, if n is equal to 1, if n is equal to 0, say if n is equal to 0, then the complex number lies in the first round of the circle. That is 3 pi by 4. Then right here, if n is equal to 0, then this is simply this complex number, this. If n is equal to 1, if n is equal to 2, if n is equal to 1, that is 2 pi, means 2 pi. First, make 2 pi angle there, after that this. So argument of this complex number is 2n pi plus 3 by pi by 4. The modulus of these two complex numbers, say 1 minus 1 plus I, 1 plus I, 1 minus I, is the same, but the angle is different. Now you can change here this complex number again. You can calculate the argument of this complex number, say minus 1 minus I. This complex number lies in the third quadrant, minus 1, minus 1, minus 1. So the argument of this complex number we can direct write here. This is third quadrant. In third quadrant, the argument is pi plus theta. So the argument of this complex number is pi plus tan inverse of modulus of b by a. So you can calculate the argument of this complex number by adding 2n pi at last. Now, if the value of theta, that is, if theta is greater or equal to minus pi, less or equal to pi, then this theta is known as principal value of argument. For example, we have a complex number 1 plus, say, minus 1 plus I. Here the argument of this complex number is, as we know that this complex number lies in second quadrant. This is minus 1, 1. And this is the argument of, that is pi minus theta. The argument of this complex number is pi minus theta. That is pi minus theta is equal to tan inverse of modulus of b upon a, which is pi minus tan inverse of b upon a is, that is tan inverse of 1, which is pi by 4. This is 3 pi by 4. So argument of this complex number is 3 pi by 4 plus 2n pi. But if the value of theta lies between minus pi to pi, then this is known as the principal value of argument. So putting n is equal to 0 here, if we put n is equal to 0, so argument of z will be 3 pi by 4. And this 3 pi by 4 lies between minus pi and pi. Therefore, we can say this is the principal value of argument. This is the argument as well as the principal argument of the complex number. Now, if we have a complex number like this, Now, if we have a complex number like this, z is equal to minus 1 minus I. Its argument is pi plus pi by 4, because this complex number lies in third quadrant, where the argument is pi plus theta. So this is 3 pi by 4. Here this is pi minus 10 was 4 pi minus 3 pi by 4. This is 5 pi by 4 here. This is 5 pi by 4 plus 2n pi. So this is the argument of this complex number. Now, if we check 5 pi by 4 not lies in between minus pi and pi. Therefore, we can say this is a not principal argument. It is the argument, but not principal argument. For such conditions here, if the complex number lies in first quadrant, then it is principal argument here. We can write here principal argument is theta, because this is an acute angle that lies between minus pi and pi. If the complex number lies in second quadrant here, then its argument is pi plus theta. Again, it is, if the complex number lies in second quadrant, its principal argument is pi plus theta. Pi plus theta. Now, if the complex number lies in third quadrant, we know that this is pi plus theta, and that not lies in between minus pi and pi. So, if the complex number lies in third quadrant here, we define its principal argument as theta minus pi. We are taking the angle in clockwise direction. So its principal argument is theta minus pi. Similarly, if the complex number lies in fourth quadrant here, its principal argument is minus theta. Thus, in general, you can remember the values of principal argument. If it lies in first quadrant, then its principal argument is theta. If it lies in second quadrant, then its principal argument is pi minus theta. If the complex number lies in third quadrant, then its principal argument is theta minus pi. If the principal argument lies in fourth quadrant, then if the complex number lies in the fourth quadrant, then its principal argument is minus theta. So here, the principal argument of this complex number, this is the argument of this complex number. So this complex number lies in third quadrant. Therefore, principal argument is theta minus pi. Theta is pi by 4 minus 5. This is minus 3 pi by 4. And minus 3 pi by 4 lies in this given interval. Therefore, this is the principal argument of this complex number. So this is the procedure how to find the argument and the principal argument of the complex number. Now, we will discuss here the polar or trigonometric form of a complex number. So what is polar or trigonometric form of complex number? As earlier we discussed, ordered pair in argand plane represents a complex number. So x comma y in argand plane is a complex number. So if this is the point P here, x comma y, this distance is y and this distance is x from the origin, and this is modulus of z. Say this is r, and this is theta, where theta is the argument. And this is 90 degree. So, and this is A. Thus, OAP is right angular triangle here. So, in a right angular triangle here, polar form or trigonometric form means we have to write the complex number in terms of sine and cos. So, cos theta, as we know that from earlier classes, this is base upon hypotenuse. What is base? Base is x. And what is the hypotenuse? That is modulus of z, that is equal to r. So, which implies x is equal to r cos theta, where theta is equal to, this is the argument, this is equal to tan inverse of modulus of b by a. And sin theta, as we know that sin theta is perpendicular by hypotenuse, that is y upon r, which implies y is equal to r sin theta. What is r? Actually, it's the modulus of the complex number. As we know that this point is a complex number x plus iy. Now, what is x? R cos theta. Therefore, x is equal to r cos theta plus I times r sin theta. So, taking r as a common, we have cos theta plus I sin theta. This is known as the trigonometric or polar form of the complex number, where r is the modulus of the complex number and theta is the amplitude or the argument of the complex number. Now, when you have to write the complex number x plus iy in polar form, that means you have to write this complex number in terms of cos and sine. That is r times cos theta plus I sin theta. This x plus iy, this is known as the Cartesian form of complex number, and this is known as trigonometric form of complex number. Let's do an example related to the same concept. For example, find the polar form of, that is the trigonometric form of the complex number z is equal to 1 minus 1 plus I. So, we have to write this complex number in polar form. So, this is the Cartesian form of complex number. Here, we have given the complex number 1 minus 1 plus I. This is known as Cartesian form. We have to write this in polar form. Means we have to write minus 1 plus I in terms of r cos theta plus I sin theta. Thus, we have to find the value of r, that is nothing but the modulus of the complex number. And we have to find the value of theta, that is nothing but the argument. So, modulus of z here, that is r, as we know that is equal to square root of 2 minus 1 square plus 1 square. Minus 1 plus I, this is the complex number that lies in second quadrant here. As we know that the argument of this complex number is pi minus theta. So, we can write here argument of z is pi minus pi by 4, that is 3 pi by 4. This is the principal argument here. So, we can put, or we can add here 2 and pi. So, put these values, argument of z and the modulus of z in this given equation. Therefore, minus 1 plus I will be equal to root 2 times cos of 3 pi by 4 plus 2 n pi plus I sin 3 pi by 4 plus 2 n pi. So this is the polar or trigonometric form of complex number. Now, if the angle here is the principal argument, then its polar form may be minus 1 plus I is root 2 times cos of 3 pi by 4 plus I sin 3 pi by 4. So this is the polar form of the complex number. So every complex number that is of the form of, or that is in Cartesian form, you may convert in polar form by following the same procedure. Thank you very much. That is all for the today's lecture.